Okay, so today's topic is going to be an intro to logarithms, and really this is like 3 days worth of lessons. Today we're going to just introduce what a logarithm is, because it's a fairly brand new concept here. Tomorrow we're going to talk about some rules that apply to them. And do you guys still have the data sheets, the formula sheets I would have given you at the beginning of the year? Tomorrow we're going to talk about a few rules that are on that formula sheet. They're written there for you because since you guys don't really work with logarithms all that much, they're not going to expect you to memorize them. But can you see where there's some log type rules where there's log, maybe a times log b or something like that? So we're going to talk about those tomorrow. And then on Wednesday, we're going to talk about how to solve something involving logarithms. Just like we did with exponents and polynomials, how do you get x by itself? So here's just a summary slide to review the different functions we've done so far. Rational functions basically involves fractions. Do you have to graph those? No, you do not have to graph rational functions. Okay. Do we have to solve them though? That's what we spent our whole first unit on, was just practicing the algebra skills of solving. So although the functions for rationals don't have to be graphed, like this top one here, you do have to be able to solve it. So, I mean, I know it's been a while, but if I gave you like that equation, ideally you'd know how to solve this sort of thing and get what x is by itself. It may involve quadratic formula, by the way. You guys recall doing this unit 1? We'll do a review in June on it again, right? Because it's been a while. But this one you only have to solve. Okay. The rest of them you have to be able to solve and graph. Okay. If you have a polynomial function that's like, say, quadratic, you solve it using the quadratic formula. If it's linear, like say 3x plus 5 equals 2, that's a linear type equation. Then you just solve it by minusing 5 from both sides and then divide by 3. One of the big things I've been focusing on is knowing what the graphs look like. So hopefully you could look at this equation here and roughly tell me what the graph looks like. Last week we focused on exponential functions. Same thing. You should be able to solve it. You should be able to graph it. So today and the rest of this week we're doing logs. And then next week is a week devoted to sinusoidal. Fair enough? So, what's a log? Who took Chem 20? You took Chem 20? You took Chem 20. Okay. Do you guys remember the formula in Chem 20 that the pH is equal to the negative log of a number? Like, that might be the only experience I imagine most of you have with logarithms. Has anyone actually worked with them before at some point? Okay. So basically I'm starting from scratch here then. Here's what a logarithm is. It's an operation. Let me give you some other examples of operations. Do you know how to add or multiply or subtract or divide? Those are operations. Now, usually when you add, you take two numbers and add them together, right? Or when you multiply, you take two numbers and multiply them together. But there are some operations that just happen just to one number, like say squaring. You can take a number and square it. All you need is one number and you do the squared button. Does that make sense? Or the opposite of squaring is the square rooting button. Well, a logarithm is a type of operation. And so my goal today is to explain to you why we would need such an operation and where it gets used. So I think those are my two goals today. Explain why we need it, where it gets used. And I guess the last part is like show you the graphs and stuff. So let's just try these in our calculators. Could you guys calculate for me the log of 3? Okay, so good question. So we need to know where this button exists on your calculator. The button is right down here. You know how like there's the x to the minus 1? That's an operation. Here there's the squared operation. Right below it with other type of operation buttons is the log button. So just type in the log of 3.
0.477.
That's it. So that's 0.477. Well, can you do other operations along with it? Like, for example, could you do the log of 5 plus 3? Sure, why not? I mean, you can log and add numbers. Looks like that's about 0.903. Now, I did these two back to back to try to prove a point here. Do you see how the 5 plus 3 is inside the brackets on this particular one right here? Do you see how this next one right here has a 7 plus 1, but I didn't include brackets? What this means for the third one here is to go 3 log, just log 7 close the bracket, and then add 1. It very much implies, if you don't put a bracket, that the only thing you log is the very next number, and that's it. Does that make sense? If you put it in brackets, though, it means you have to log the both of the two numbers. So this guy here would be 3.54. Still good? Or one more, -2 times the log of 0.5. So 0.602. So at this point here, all I need you to know is that logarithms, this log button, basically means you're doing some sort of operation on a number, kind of like square rooting, right? Like if I asked you to square root the number 58, it'll give you an answer. If I asked you to take 8 and make it go to the power of -1, it'll give you an answer. If I ask you to log 78, it'll give you an answer. So one of the tricky things about logarithms is that they are actually quite challenging. But if you just really approach them just as purely, it's just going to give you a number, it's really not that bad. Your calculator does all the work for you. But then you might ask the question, Shock, why should I care? Right? Like, does this get used somewhere? So I'd like to show you over the next few examples here where it gets used. You guys ever heard of the Richter scale? The Richter scale is used to measure earthquakes. If you have an earthquake that's like, say, a 9 on the Richter scale, those are like hugely, massively destructive earthquakes. If you have an earthquake that's more like a 4.2 or a 3, then, I mean, it's still an earthquake, obviously, but like it's nowhere near as bad. The Richter scale is actually based on logarithms. Let me see if I can explain how this works. The formula is y equals log x. That's the formula we're going to actually start with today. And they use a little machine called a seismograph, which basically measures how strong the vibrations happen to be. Okay. Usually what you do is you start with the vibration with a base level of 1. Like 1 is kind of normal. Well, if you guys have a calculator, can someone find me the log of the number 1? It's 0. Which means that this means that nothing special is happening, right? If the amplitude is 1, which is like what it normally would be if you're kind of using that seismograph to measure, it means that there's nothing happening. Well, if the vibrations are 10 times bigger, then we need to log that number. So what's the log of 10? Yeah. So if compared to normal vibrations of just everyday life movement, if they were 10 times bigger, it would actually be a Richter scale earthquake of 1. Let me just bump this up a little bit here. Let's say that it was 1,000,000 times bigger. So normally vibrations vibrate like this, and then they're 1,000,000 times bigger. What's the Richter scale mean? It's a 6. Once you kind of figure out the pattern, if you've tried the ones in between, this is actually 2, 3, 4, 5, and 6. You know what a logarithm does? It tells you how many zeros are after a number. How many zeros are after this number? 6. After this number? 5, 4, 3, 2, 1, and no zeros. What the Richter scale and what logarithms essentially try to do is it's a way to try to break down very large numbers. If you're going to have things that are super, super duper big, so large you require exponential notation, sometimes we use logarithms instead. And rather than telling you how big the number is, what the logarithm really tells you is how many zeros are behind the number. So if you have, like, say, an earthquake with a Richter scale of 10, it means there's 10 zeros after the number. That's how strong the vibrations happen to be. Does that make sense? That's actually what this next slide shows here, if you haven't seen this one yet. Log of 1 is 0 because you need 0 tens. There's like 0 tens digits. Whereas like log of 1,000,000 is 6 because there's 6 tens, 10 to the 6. 1, 2, 3, 4, 5, 6. Does that make sense? Let's try another little activity while we're sitting here. What if I asked you to log the number... Here, don't type it in your calculator. Could we just look at the number and figure it out? Yeah, I got 10 zeros as well. Yeah. So this is basically a way of trying to take very large, astronomically large numbers and try to break them down to like something smaller to quantify them, to compare them. Does that make sense? What happens if I ask you, though, to log 703? Can your calculator still do that? Well, sure. But it does a little bit differently here. I just want to compare something. Log of 703 is somewhere between the log of 100. Then the log of 703 would be next. And then like the next one we could work with is the log of 1,000. Yeah, it's going to be at 2 point something is what I'm getting at. Because this one has 2 zeros. This one has 3 zeros. Is this one a nice round number? Well, no. But hopefully you can kind of see it should be 2 point something. Someone want to try it for me? Just tell me what. 2.8. Okay. Does that make sense though, that idea that, you know, we can actually use this log scale in between numbers? So there's not quite 3 zeros after the number yet. There's 2 and a portion of them. Let's just try one more. If I asked you to estimate the log of this number right here, could you guess about how big that number would be? If you had to log it? It's probably going to be 6 point something because there's 1, 2, 3, 4, 5, 6. So it's somewhere between this number here, which if you had to log this number would give you a 6, and this number here, which would be 7. So yeah, I'd have to guess, you know, 6.9 probably. 6.8, somewhere in there. So to restate one of my goals is to explain to you, I guess, A, how logarithms work. I'd say that's pretty easy. Just type the stupid thing in your calculator, right? It's pretty straightforward. But to explain why they work, really what it's doing is it's taking a large number, which has lots of digits, and we're just asking you, like, how many powers of 10 are there? So 100 is 2 powers of 10, 2 zeros. 1,000 is 3 powers of 10, 3 zeros. Let me show you another example where this gets used. You guys ever heard of, like, the decibel system for, like, how loud something is? You ever heard this before? Like 120 decibels is really loud. 80 decibels is kind of loud. You ever heard that decibels before? Here, I have some stats, and I also have a picture here. So, like, if you talk at 30 decibels, that's basically a whisper. I'm doing normal talking right now, so that's probably about 45, 60 decibels. If you go to a rock concert, the loudness of how loud something is about 110 decibels. Fair enough? So the way this system works here is they made the decimal system slightly different. You log the number, but then you also times by 10. So like for example here, let's try at the bottom here first, the threshold of hearing. If you cannot hear something, basically it's as soft as it could possibly be, like there's no audible noise. You need to log the number 1. Well, how many zeros does the number 1 have? 0. Then times it by 10. 0. So that's why the threshold of hearing, if you can't hear anything, it has 0 decibels. Which kind of makes sense, doesn't it? Well, if leaves were rustling in the wind, just very, very, very faint, you could hardly hear it, you'd have to say, well, it's 10 times louder than the threshold of hearing. Well, how do you log 10? It would give you the number 1, right? Because there's 1 0. But then you'd have to times it by 10, hence the 10. Or look at this one here, door slamming. A door slamming is 10 million times louder than basically nothing. So based on that, you have 1, 2, 3, 4, 5, 6, 7 zeros. So 70 decibels. All the way up to like a jet plane. If you're 30 meters away from a jet plane, so I mean crazy loud, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 zeros. Times that by 10. 140 decibels is how loud a jet plane is.
What would you call it?
Like this number here. Let's see, that would be the hundreds, thousands, millions, billions, trillions. So 100 trillion. 100 trillion. Now this is 100 trillion times louder than basically the softest thing that a person could hear. Does that make sense? So like, did you guys hear that? You can hear it? So I mean, imagine the softest thing that you could basically hear. Find that threshold where, like, if I was making a sound, you wouldn't be able to hear it, and then make it 1 trillion times bigger than that. That's what a jet engine does. So, okay, so now let's get to maybe more of the graph part, because one of the things I have to teach you is what these graphs look like and the properties. So grab a graphing calculator. We've got a few things we should talk about here. We need to graph the graph log x. So go over to y equals, get rid of all the old stuff that's in there. If you have your plot on for some reason, by the way, sitting up top there, get rid of the plot. We don't want that anymore. And just type in log, but then x, because we're going to log an unknown number. We could log 1. We could log 1,000,000. We could log 100 trillion. So, and just do a nice little zoom 6. And we'll talk about what this graph looks like. This is what a logarithm graph looks like. Anybody else able to get that on the calculator?
I missed what you typed in.
So go to y equals.
Yeah.
And just type literally log x. X because we could log any number, right? We could log 3 or 4 or 7. You guys able to get this graph? I just went with a 10 by 10. Okay. You need to be smarter than your graphing calculator. I say to kids a lot. Your graphing calculator makes it look like the graph looks like this. It appears the graph starts basically here and does that. Okay. But that's based on one of the limitations of your graphing calculator. Your graphing calculator is unable to draw this line going straight down, because that's actually what's occurring. This graph is actually going straight down. So straight down that literally this line is right on top of the axis. So that's actually why we're not seeing anything probably. So don't just leave your graph looking like this little bit right here. If you do this, I won't mark it as correct because this graph actually extends all the way down. Essentially, it's going perfectly straight up. That's what a logarithm graph looks like. I have to talk about how this works for a little bit here. I want to go to a table of values. And this is probably as good a place as any to start, right around 0. If I ask you to log the number 1, how many zeros does the number 1 have? I'd say it doesn't have any, actually. How many does the number 10 have? Well, 10 gives you 1. What would the next number for x be on here that would get me like the next whole number for y?
It'd be 100.
100, yeah, because 100 would give you 2. 1 would you get up to 3? 1,000. Right? So what's happening is this graph growing? Yeah, it's growing. But it's growing very, very slowly. Does that make sense? By the time this graph gets as high as 5, that's going to be 10,000. No, 100,000. Because 100,000 is when you have 5 zeros. Does that make sense? So this graph goes very slowly. But here's the other thing. You can actually log a decimal number. Give this a try here. Find me the log of 0.1. It's actually -1. Bear with me. Let me show you a few more things here. Log 0.01. It's -2. Log of 0.0001. Before I press enter, anyone want to hazard a guess? Yeah. This is 1 0 right here, -1. There's 2 zeros right here, -2. 1, 2, 3, 4, 5, 6. Oops, sorry, you miscounted one. But it would be -6. You just miscounted one. Yeah. You can actually log decimal numbers. As long as the decimal numbers have zeros in front of the number, it actually becomes a negative. Here's the one thing that you cannot do, though. You can't log 0. That's actually impossible to do. It's also impossible to log a negative number. You can't log, say, -2. That's also not possible. Yeah. So this is actually the very first time, and the only function that you guys need to know about, where the domain is not element of the reals. If you go to that table like Shodi was talking about here, all of these numbers in the negatives are basically errors. So let's talk about a few of these things here. The x-intercept actually does exist. The x-intercept is right here, and it is at 1 with 0. Because the number 1 has no zeros behind it. But there is no y-intercept. This is the first graph I think we'll ever have talked about where there is no y-intercept. That's not how this graph works. There's actually an asymptote, but I'm going to do that one in a second. Your domain essentially is like there are no numbers over here whatsoever. Like this whole half of the graph is missing. Have we encountered a graph kind of like that before, where like the whole half of a graph is missing? What did we do last week? What kind of graph did we do last week, though? Exponential looks something like, I don't know, this maybe. It never goes on this half of the graph down here. Exponential and logarithmic graphs are actually very similar in a way. Rather than on an exponential graph, basically saying you can't have the whole bottom half of the graph, logarithms have a similar property in that you can't have any of this left hand inside of the graph. Remember that analogy I gave, which hopefully made sense, where like you lose half your stuff, and then you lose half your stuff again, and you still lose half your stuff. Maybe you've got divorced 4 times, and you lose half your stuff, right? Do you still have stuff? Technically, you're not in the negatives, right? If you just keep losing half, you used to have $100, now you have 50, then you have 25, then you have 12 and a half, right? But you're never actually going to be negative. That's what this graph that we worked on last week does, where the graph keeps getting smaller and smaller, but it never actually goes into the negatives. Well, this graph does a very similar thing. You cannot actually start with an x value in the negatives. That's not possible. So the domain is x is greater than 0. You can use an x of 1 or 2 or 3 or 4 or 5 or 6. But can x be a negative number over here? No. It also can't even be 0 itself. If you try to let x be 0 itself, it gives you an error. Such a domain. Let's go back to the asymptote. You know how in this graph right here, the asymptote was basically the axis? We would say that y's asymptote was at 0. Anyone want to hazard a guess as to what our asymptote is in this graph right here? It's not where y equals 0. It's where x equals 0, yeah. X basically will never get close to 0. It's always going to ride right next to this line right here, but it's never actually going to touch this straight up and down line. It's almost like take the graph and like shift it sideways in your head. Can you almost imagine like looking at this graph like this, turning your head sideways? Can you see an exponential graph out of it there? So basically the properties are backwards. The range then is anything you'd like. The reason why it's anything you'd like is this graph is going to go straight down infinitely. So can you find an answer down here, like down there or there or there? Sure. Will this graph ever get this high up here? Yeah, but it's going to take its sweet time. Does that make sense? This graph will grow, but it's going to take a long while. It's then possible for it to have a root, but the only root is going to be your x-intercept. Have I used the word roots with you guys before? If I haven't used it before, a root is another word for an x-intercept. So your roots really are just what we wrote up there. All right, last little bit. Let's talk about the end behavior. Which quadrant is it starting in?
4.
Yeah, this is actually quadrant 4. It does not cross over here into quadrant 3. So it actually starts in quadrant 4, and as it goes from left to right, it ends up going into quadrant 1. It's a very unique graph. Most other graphs will end up going, like, say, across the grid, but this one will actually start on the positive side and just grow up and over. This whole left-hand side, it's impossible. So quick summary of the most important thing you need to know is your domain. Previously, you were allowed to just pretty much always say x is element of the reals. This is your exception. Okay. Let's try another one. What if we make it 2 log x? How's that going to change things? Well, if we do 2 log x.
Looks the same.
Pretty much. Except I want to point out one really key thing here. See how 0 is at 1 with 0? 10 is not at 1, it's actually at 2. Because what you end up doing is you end up, you know how 10 would have normally been, it has 1, 0? But then you times it by 2. Does that make sense? So if I were to type in the number 100, it would be 6. Because normally it would be at, 100 would actually be at 4. Does that make sense? because 100 has 2 zeros, and then 2 times 2 would give you 4. So then 1,000 would be 3. It would be 6, because then 1,000 has 3 zeros times by 2. Then it would be 6. So the graph that we have basically is doing this. It's got the exact same pattern. It appears as though this is all you're supposed to draw. Okay. But that's not true. Your graph is actually dropping straight like a rock, straight vertically downwards. Please make sure you include that. It's super important, because that graph does exist there. Just your calculator doesn't seem to have it showing up, that's all. So then what are our properties? Well, your x-intercept, if you just even try to look for it here, is at 1, just like it was last time. How many zeros does the number 1 have behind it? 0. Hence, if you have the number 1, there are no zeros behind it. If you have the number 10, there's 1 zero behind it. Y-intercept doesn't exist. Asymptote, is there one? Yeah, it drops straight down, so then this is where x equals 0. The reason being is that x has to be greater than 0. You can't have negative numbers on this graph. This whole left-hand side, you're out. Range?
Maybe the same as last one.
Yeah, element to the reals, yeah. Will this graph ever reach the very, very highest of highs? Sure, it's just going to take time, right? Will this graph end up being down here at some point? Yeah. Roots, by the way, are just the same thing as x-intercepts. And the end behavior is the same as we just had last time. Typically, it goes from 4 to 1. So far, so good? Okay, I want to change this one up a little bit. Let's not put the 5 right here. What I'd like to do is, I'll just rewrite the whole thing. Can we do the log of, in brackets, x minus 5? So I'm very clearly putting the x minus 5 in brackets. I want to talk about what this graph does. So go log, open the bracket, x, then minus 5, then you can close the brackets. Need a graph that looks like mine, where there's like a little piece of line sitting over here. Anybody get that one? So you might be inclined to draw the graph kind of like that and just kind of stop. But this is where your calculator again has issues. You know how your calculator was having issues drawing that line vertically straight down because the axis was in the way? Your calculator also has issues drawing lines perfectly straight down. Your calculator is programmed not to be able to draw a line straight up and down. It's supposed to always have to either go up or down at some sort of angle. Now, I don't know exactly how the calculator is programmed or the whys behind it, but here's what I can tell you though. The graph, although the calculator makes it appear like it's stopping there, the graph is dropping straight off a cliff like the other one was supposed to. So even though your calculator might not show that line straight up and down very well, you should still actually calculate it. And I want to show you why this might be tricky here. I'm going to go second calculate the value when x is 6. I'll just do that one first. See how it puts the cursor on the graph right there? Well, let me try a number smaller than 6. I'm going to calculate the value at 5.1. Boy, it sure looks like that's kind of where the graph starts, right? What would be smaller than 5.1? I want to go just slightly more than 5, though. So why don't I try like 5.01? Do you see how the cursor doesn't appear to be on the graph, but it still shows up? It's a weird anomaly about how these calculators function. It's a good choice of word here. Where this graph actually keeps going down, but your calculator just is incapable of drawing a line that steep, essentially. If I try to calculate the value at 5.001, like that, see how it puts the cursor right there? There is a graph there. It's just your calculator doesn't actually put the graph straight down. Does that make sense? So, okay, let's talk about the properties then. Is there an x-intercept? Yeah. To find it, just do what you always did before. Find the 0 button. Go on the top and bottom of the thing. That might be the hardest part to find, is to figure out where the cursor is. I found it at 6 and 0. Is there going to be a y-intercept if this graph just drops directly off the face? Like just no.
Well, what happened on that one? Why did it say there's no equals y?
Oh, you have an error on your calculator? Because look, here's the y-axis right here. Right. Is this graph ever going to cross this axis right here? Well, if it's dropping straight down like a rock like this, then no, it's never going to. We can try that. Second, calculate the value when x is 0. You know what your calculator is going to do? It's going to say x is 0, and it's going to say y equals nothing. Like it literally is going to leave the y equals spot here blank, saying the graph doesn't exist over there. You asked me to find where the graph is along this axis, and the calculator is saying it doesn't. You know how the answer, there is no answer, was valid before? You know the same thing right here. If I asked you to say find where x is equal to 0, you'd say it doesn't ever equal 0. So not applicable. Anyone want to take a guess as to what our asymptote's at? Yeah, it's actually where this minus 5 came in here. If you go to your table of values, you'll notice that 5 is the last number that you cannot use, and 6 is the first number you can use. Some people think that it has to be greater than 6, but that's not true because you can actually use 5.9, 5.1, 5.01. It's actually 5 right here. That's the issue. So your asymptote is where x equals 5, and you have to be greater than 5. And that is a direct result of that little number sitting right there. Range, anything you want it to be. This graph will go from the lowest of lows to the highest of highs. It just doesn't do it on the left-hand side of the graph. That's all. Your root is your x-intercept. Your end behavior, like as before, goes from 4 to 1. Does it always have to go from 4 to 1? There's actually a way I can change that. If I were to do this graph here, you know how it was an x minus 5? If I make it an x plus 5, it would actually take the graph and put it over here instead. And then there would possibly be a y-intercept. So I cannot guarantee you that there is never, ever, ever a y-intercept, because you could kind of slide that graph over. What I can guarantee you, though, is that there is always a certain stopping point in the graph where like that part of the graph doesn't exist. Does that make sense? Okay. What I want to show here on this slide here is how similar these are to exponential graphs. Do you guys recall doing an exponential graph where it goes really close to the axis and then just shoots up? Well, maybe you can see the similarities in this green picture, which I guess probably isn't green for you guys, but in this green photo right here and in this log photo. Do you guys see how like if you turned your head like kind of tilt at 45-degree angles, how it kind of has a similar pattern to it? You guys see the similarities? The green graph, the whole bottom half of the graph doesn't exist. Whereas on the red graph, the whole left-hand side of the graph doesn't exist. There's actually a similarity between them. Okay. I want to talk about this graph now. This is called lawn. You pronounce it L-A-W-N, as though it's like your front lawn. This is actually a very unique kind of logarithm. So unique that it's given its own symbol. Can you guys see how there's ln right below log? Lawn is a particular kind of logarithm that does exactly like what a log does. It goes like ln of 8 is a number. I just want to try a few examples though. Like say ln of 1. Well, how many zeros is after that number? Say there's none. Okay, so far so good. Ln of 10. How many zeros are behind that number? Ah, crud. Okay. Ln of 100. Oops, I just screwed that up. Ln of 100. Well, if this was a logarithm, you'd think it'd be 2, but it's not. Okay. So this is called the natural logarithm, and it's actually based off of the number e. Do you guys remember talking about the number e a while back? It's actually like a number of like 2.718. And I mentioned that there are a lot of things that naturally grow according to a natural logarithm. This one here looks very similar to a log graph. If I go graph this thing and just do ln of x, see how it looks kind of just like good old-fashioned graph that we talked about before? People have discovered that this particular graph right here is actually like the natural rate of growth for many things. And it's actually based on this number e. I'm not going to get into this part until later in the course because I don't want to bite off more than we can chew. But essentially what happens is that this is a logarithm. It's a type of logarithm that's similar, and it has what's called a base. Sometimes you see logarithms written like this, log with like a little number down here of 3, or log with a little number down here. We're going to talk about that little number on another day. But just so you're aware, what ends up happening is if that little number is the number e, then it's called a ln, which is a natural sort of thing. So I'll focus on that more another day if that's okay with you guys. But I just want you to be aware that there are actually 2 logarithms you can graph. There's the log one and the ln one. Here's where this matters to you. You know how we can do data and you can do like stat, calculate, and you can go down and you can do a logarithm? You should be able to do linear, quadratic, cubic, quartic, and then eventually get down to exponential. Some people think that they're supposed to do logistic for logarithms, and that's actually not what it is. If you need to do a logarithm, we actually always do this one right here, ln reg. That stands for a natural logarithms regression. Okay, everybody clear on that? Don't use logistic. It's going to give you a totally wrong answer. Even when you use logs, we're using ln because ln is actually a special type of logarithm. Like, would you agree that the graph I just showed you here pretty much looks like a logarithm graph like I showed you before? Okay. You might ask, where in the world does this whole natural logarithm thing kind of come in? You know what? For the longest time, I, as a teacher, actually had no answer for this. And then one day, it was actually when Melissa and I were taking Kinsey Ann to the doctor. And the doctor showed me a chart, and the math geek in me all of a sudden went, oh my goodness, because they showed me a chart that looks like this. This is how long a baby is supposed to be compared to how old they are. And they were showing me where Kinsey Ann felt on like the, like when you're a little baby, you go to the doctor, they do the measurements to make sure they're healthy. You know what I'm talking about? And they plotted Kinsey Ann's growth on a graph. And all of a sudden I looked at the graph and I was like, that's a logarithmic graph. And I had no clue that you use that for that sort of stuff. So this is actually a place where you'd find this. You'd see it in growing things, where like when you're a little kid, you kind of grow at a fairly decent rate at first, but then it starts to like flatten out. Do you guys see how like this graph right here, it's starting to flatten out a little bit? You guys are now 18 years old. Are you still growing? Well,
Pretty flat.
but like, yeah, like you're not growing all that much anymore. Does that make sense? Right? This is like when you're born. And then as you're born, this is when you're 1, you're 2, you're 3, you're growing higher. And at some point, it's basically flattened out. Does that make sense? I found another graph, just to illustrate the point, about head circumference. Same thing when they were measuring Kinsey Ann's skull all the way around. When you're little, when you're born, your head circumference is about this. And then as you grow quite fast for a while, and then it flattens out over time. These are logarithmic graphs. So a lot of things that grow will actually grow according to a logarithmic graph. But what we'll probably do is rather than doing a log graph, we'll probably do a natural logarithm because that usually models its growth better. And it uses that special number from Euler called e. So, in case you're wondering why to care, that's actually the reason. Wait, what do I got left? Just more pictures of how these graphs work. We're going to talk about this tomorrow, I think. Tomorrow what we're going to do is we're going to talk about how exponents and logarithms have such similar characteristics that there are some rules we need to learn. And this is one of them. It involves talking about how logs have a base down here. But I think, is this my last slide?
No.
Do I have more than this?
Like 4.
Okay. I really should have put this one last. This is more of like a preview for tomorrow. We're going to talk about how logarithms and exponents actually have very similar characteristics. So maybe I'll just leave that till tomorrow. Okay, let's do one more graph here, and then I think we're nearly at break time here. What if I made it -4 ln x? Let's try graphing that. So I'm expecting it to be a logarithm, right? If I make it -4 ln x, what happens to the graph?
It's going down to it.
It goes downhill. That's all. So even though the graph looks like it's starting right about here, the graph is actually going up to infinity and then kind of going downhill. The biggest difference then is rather than this being a growth graph, this is a decaying graph, where just the graph is slowly but surely getting smaller. Does that make sense? The biggest difference is your end behavior. You're actually starting in quadrant 1 and ending in quadrant 4, because here's where you're starting, and down here is where you're finishing. So it is possible to actually have the graph go downhill. So, okay, here's a typical kind of diploma type question. This is actually out of a textbook, but what they might do is they might ask you to match graphs. So here's some equations, here's some graphs, let's match them. So let's look through them one at a time here. What's happening in graph A? Don't even type in your calculator, just think about properties. What's happening in graph A? Is it growing or decaying?
Decaying.
It's going downhill. But is it doing it according to a logarithmic or an exponential type thing? And I would say it's happening according to a logarithmic. Because do you see how it's starting on the axis and just dropping like a rock? That's what a log graph would do. So we need to pick out a graph that would have a decaying log. That would be 4. The reason why it's number 4 is see how there's that -2 in front of it? The -2, it's the negative that makes the thing go downhill. Remember the term leading coefficient? It's got a negative leading coefficient, so it goes downhill rather than uphill. What about B? What's happening in B? Decay or growth? Growth. But this is happening according to like how an exponent works. So the one that has an exponent growth is number 1, because it's got a positive 5. C also has growth, but do you see how it grows a little bit differently? It's growing as though the bottom, like the left-hand side of the axis, doesn't exist. So this one here has to be one that has logarithmic growth, so that'd be number 3. And then this one's going to have to be number 2, which is an exponent that's going down and decaying. Why does this one number here, why does this one go downhill? There's no negative sign. It's the decimal that does it, yeah. So the thing I want to point out here is if you want to have a decaying graph, as an exponent, you need a decimal. But as a logarithm, you actually need a negative. Okay? I think one more picture just talking about how this is a growth graph, and here's a decay graph, that's all. That was my last slide now?
Yeah.
Okay, so quick summary of the day then. Logarithms are very odd sorts of functions. You might question why we need them. And to be honest, for the longest time, even to this day, I still kind of question, like, yeah, they're not that relevant. But that being said, I mean, there is a few places where they're useful. Sure, right? So essentially what a logarithm does is it takes a large number and makes it smaller based on how many zeros are behind it. The number 10 has 1 0, so 10 becomes 1. 100 is 2 zeros, it becomes 2. 500, well, it's not exactly a perfectly round number in the same way, right? So like 500 is somewhere between 100 and 1,000. So it probably is 2.5. Does that make sense? So you can do it with in-between numbers. The one number that you cannot try to logarithm is a negative number. It doesn't exist. That's why the whole left-hand side of the graph is gone. You also can't try to logarithm the number 0, by the way. So the big change to these graphs is now your domain is bigger than something rather than your range. So this is the first time that you can't just default and just say x element reals. You can say y element reals, but you actually have to figure out where your x graph asymptote starts, where it just basically either shoots up or it maybe comes down. You can have degrowth, you can have decay. Yeah, that's basically today's lesson. Tomorrow we're going to talk about some laws on logarithms. And so we'll use some laws on your formula sheet. Maybe I'll just do a quick preview here. These are the rules right here that are on your formula sheet. And we're going to have to talk about how to use them. And especially we're going to want to talk about how there's a little number sitting down here in the corner. Okay. We didn't talk about that today because it's already been an hour. But eventually I'll talk about how you can deal with this little number sitting down there. That's my lesson. Any questions? Okay, in a second here, take 5. Things to work on. 1, if you're behind still, I'm disappointed, but you should catch up on stuff first, okay? There's a new assignment, number 9. You can kind of get started on a few of the questions if you'd like. I was really intending for Thursday to be the main work day for that, but you should probably do a little bit before then. And then the other thing is I'm going to ask you guys to do some questions in your journals again this week. Please do them. It's not for my benefit. It's definitely for yours. I would recommend, I gave you 2 new worksheets to do. This is pretty fair minimum again, but can you guys do 5 graphs of logarithms? And then 5 of the logarithm laws that we'll learn about tomorrow. 5 of each. I'd say that's got to be the bare minimum. I'd also recommend for some of you guys who struggled with doing the solving the exponential ones, like say on the test there was a question that looked like this. Square root of 2 equals like 1 over 4. And you have to like solve that sort of stuff. Or maybe 2 bracket 3 to the power of x equals 27. And you have to solve some of those things. Maybe you should practice a few more of those as well. So, anyways, why don't I stop here? Take a break. And then when you come back, find something to work on. You got half an hour. So. Sound good?